Welcome to the third part of this module. Let's start with feature selection. Feature selection is the process of selecting the most relevant and informative features that contribute positively to the model's performance, while removing irrelevant or redundant features. This process improves accuracy, reduces training time, and prevents overfitting. Why feature selection is important. Enhances model. Accuracy, removes noise, and focuses on meaningful features. Reduces overfitting. Eliminates unnecessary variables that might introduce noise. Speeds up training. Fewer features mean faster computations and shorter training times. Improves interpretability. Makes the model easier to understand and explain. Challenges in feature selection. In real-world applications, it is often unclear which features are irrelevant. Some features might appear useful but do not contribute to the target variable. Automated methods are often required to systematically identify key features. Feature selection approaches. 1. Low-variance feature elimination. Concept. Removes features with little or no variation across data points. Why? If a feature has low variance, it provides little information for model predictions. Example. A column where 99% of values are the same can be safely removed. Second. Univariate feature selection. Concept. Selects features based on statistical tests. How? Each feature is tested against the target variable to determine its relevance. Methods. Chi-square test for categorical features. ANOVA, analysis of variance, for continuous features. Mutual information, measures dependency between variables. 3. Recursive feature elimination, RFE. Concept. Iteratively removes the least important features. How? A model is trained and features are ranked based on importance. The least significant ones are removed step by step. Example. Used in logistic regression, support vector machines, SVM, and decision trees. Fourth feature importance, embedded methods. Concept. Feature importance is calculated directly from the model. How? Models like random forest, XGBoost, and decision trees assign importance scores to features. Example. In random forest, features contributing more to tree splits are ranked higher. In lasso regression, less important features get 0 coefficients and are removed. Example. Feature selection in precision agriculture. Imagine predicting crop yield using these features. Soil moisture %. Temperature, degrees Celsius. Rainfall, millimeters. Soil type. Pesticide used. Crop type. Farmer's name. Feature selection. Farmer's name is irrelevant and should be removed. Soil type might be categorical but could be useful. Rainfall and soil moisture may be correlated, so one might be removed. This is a process where important features that contribute positively to the interested output or performance of the model are automatically or manually selected. Irrelevant features or redundant features do not add to the target concept. In many real-world applications, irrelevant features are often unknown. Weeding out these irrelevant features allows the model to learn from the most important features for better predictive performance. Principal Component Analysis, PCA. Principal Component Analysis, PCA, is a dimensionality reduction technique used in machine learning and data analysis to simplify complex data sets. It is commonly used for data exploration, noise reduction, missing value handling, and visualization of high-dimensional data. Why use PCA? 1. Reduces high-dimensional data. Converts large feature sets into fewer principal components while preserving most of the information. 2. Improves computational efficiency, reduces the number of variables, making machine learning models faster. 3. Removes redundancy, eliminates correlated and irrelevant features. 4. Helps in data visualization. High-dimensional data, e.g., 100 features, can be transformed into 2D or 3D for visualization. 5. Enhances predictive models. Identifies the most influential variables that contribute to prediction accuracy. How PCA works. PCA transforms a dataset into a new coordinate system where I, the first principal component, PC1, captures the highest variance in the data. The second principal component, PC2, is perpendicular, orthonormal, to PC1 and captures the second highest variance. Third, subsequent components capture decreasing variance, ensuring data compression. Example, PCA in precision agriculture. Problem. A farmer collects data on soil properties, temperature, humidity, rainfall, pH level, and fertilizer use. With 20+ features, the dataset is too large for visualization and efficient processing.
Solution using PCA. 1. Standardize the dataset, mean equals 0, standard deviation equals 1. 2. Compute the covariance matrix and eigenvectors/eigenvalues. 3. Select top 2 or 3 principal components that retain most of the information. 4. Use these new components as input for machine learning models instead of the original 20+ features. Outcome: PCA reduces the dataset while maintaining key information, leading to faster training and improved predictions.
Notes on PCA. PCA is a tool for data exploration. It helps to deal with noisy data, missing variables, unbalanced data, as well as helps to simplify visualization of data with higher dimensions. PCA is a compression technique that reduces the data of higher dimensions to 1 or 2 or even 3 dimensions for effective data exploration, cleansing, and visualization. It transforms linearly correlated data to independently distributed, uncorrected data. It contributes to the overall success of predictive models by selecting the most influential variables that influence the success of the predictive model. The PCA fundamentally uses the principle of singular value decomposition, SVD. SVD is the decomposition of the covariance matrix, M, semi-positive matrix, to 2 principal components representing the eigenvectors and eigenvalues. The first principal component is the direction of higher variability, and the second is the orthonormal direction. Most of the time, the first principal component is the most important one that contains consequential features that are most relevant to predictive models. Selection of the consequential features are chosen based on components, features with higher variance always depicted on the explained variance ratio plot. The explained variance ratio plots show how much data is lost and how much data is relevant to the predictive model. Class imbalance. In most real-world datasets, distribution of instances in a class is highly imbalanced. Class imbalance occurs when there is a disproportionately large amount of data of one class, majority class, and very few instances of the other classes, minority classes. This is not because of errors in data collection, but simply due to natural occurrences. Class imbalance causes misclassification or overfitting. The basic solutions of class imbalance are sampling techniques consisting of random oversampling and random undersampling. Random oversampling solves the problem of class imbalance but poses risk of overfitting. Random oversampling is when a minority class is duplicated at random until it equals the majority class, while random undersampling depletes the majority class at random until it matches the number of the minority class. However, there is a potential loss of information during depletion. 2 typical remedies to cushion these drawbacks are SMOTE technique, which stands for Synthetic Minority Oversampling Technique, and ensemble-based method. Model evaluation. Model evaluations are methods in which our models are evaluated. Model evaluation answers the following questions. 1. How to choose the best model. 2. How do I select optimal tuning parameters? 3. How to choose the best features. Model evaluation procedures are training and testing on the same data. This is a classic cause of overfitting. This is not very useful. Train test split. This gives a better performance than the first but less than k-fold cross-validation. However, in most cases, it is useful because of its simplicity and speed. K-fold cross-validation. This systematically creates k-train test split and averaging the result together. Hyperparameter. Tuning. Tuning strategies are often referred to as searching a space to find optimal hyperparameters values for a model. Typical examples of hyperparameters values include the C in logistic regression, minimum number of samples at leaf node, maximum depth allowed for decision tree model, number of estimators in random forest model. There are 2 generic strategies, namely grid search and random search. Grid search. Grid search searches exhaustively through a specified subspace to find the optimal combination of parameters. However, it is computationally expensive in time and memory. This has been used in several studies to overcome the chance of overfitting and improve the performance of models. Random search. Random search is different from grid search because of its method of search. As its name implies, it searches through the specified subset of parameters randomly. This method reduces time consumption, but it does not guarantee finding the optimal combination of parameters. Performance measure. A performance metric is a quantitative measure used to evaluate the effectiveness and accuracy of a machine learning model. In the context of agriculture, where machine learning is applied to tasks like crop yield prediction or disease detection, performance metrics help assess how well a model performs on a given task. The choice of metric depends on the problem type, e.g., classification, regression. Common performance metrics in agriculture includes 1. Confusion matrix. A powerful tool that can be used along with other performance metrics is a contingency table or confusion matrix or contingency matrix. Figure 3.5 describes a confusion matrix. It illustrates the accuracy of the solution to a classification problem. The confusion matrix shows clearly the performance of the model disintegrated into true negatives, false positives, false negatives, true positives. From figure 3.5, the row depicts the actual class and the columns depict the predicted class. Tn, true negatives, is the number of negative examples correctly classified. Fp, false positive, is the number of negative examples incorrectly classified as positive, or if the outcome from a prediction is positive and the actual value is also negative. Fn, false negative, is the number of positive examples incorrectly classified as negative, and Tp, true positive, is the number of positive examples correctly classified, or if the outcome from a prediction is positive and the actual value is also positive. Second, accuracy. This is one of the most popular performance metrics. It focuses on the overall effectiveness of the model. Accuracy is summation of Tp, true positives, and Tn, true negatives, over the sum of positive and negative examples as computed by equation below. Accuracy equals true positives plus true negatives divided by plus p plus n. Third, precision. Precision describes the fraction of truly positive outcome out of the number of total outcomes. Precision defines the purity of learning algorithm performance. Precision equals Tp divided by Tp plus Fp. 4. Recall. Recall describes the fraction of truly positive outcomes out of the number of total predicted positive outcomes. Recall defines the sensitivity or completeness of performance by a learning algorithm. Recall equals Tp per p, sensitivity. And specificity equals Tn divided by n. ஐந்தாவது F-score. The F-score is the metric that combines the trade-off of precision and recall. Receiver Operating Characteristics, ROC. Classification performance is evaluated by using area under ROC curve, AUC. The ROC is often preferred to accuracy because research realizes that simple classification accuracy sometimes gives poor performance metric results. Receiver Operating Characteristics graph is a standard technique for visualization and selection of machine learning models. ROC can be used in evaluating and comparing classification machine learning models. The figure depicts the ROC, a two-dimensional graph where x-axis represents the percentage of false positive and y-axis represents the percentage of true positive. The ideal point on the ROC curve is 0,1. It means all the positive examples are classified correctly and no negative examples are misclassified as positive respectively. The ROC curve represents the trade-off between values of TPR and FPR. At y-axis, true positive ratio. Sadavitham dp samam dp by f and plus dp. At x-axis, false positive ratio. Percent fp equals fp divided by tn plus fp. Area under curve, AUC. AUC is a more sensitive test than overall accuracy. The AUC depicts the portion of the area of the unit square, with a value always between 0 and 1.0. Every good classifier should have an AUC score above 0.5, since random guessing produces the diagonal. We have come to the end of this module. Thanks for staying till the end.